Alright, so in this video we're going to talk about a very specific compound, benzene. So benzene has the chemical formula C6H6 and looks like this. So it's a ring complex, and so it has these double bonds that go in the ring. So we do have a structure that has resonance, and because of that it makes it highly unreactive. However, this is an important compound because it is used as a precursor to a lot of different compounds that we use. It is rather toxic though. So benzene has 3 alternating double bonded carbons. Now I want to be very clear about this though. Yes, when you look at the structure, you're going to see these alternating double and single bonds. However, you have to remember that this has resonance. It has a good deal of resonance. So it can look like this, or it can look like this. So if you remember, what happens when you have resonance is that the electrons go in between the bonds. So yes and no. It has a very high degree of unsaturation. There's only 6 hydrogens on there. It has no isomers. And it does not readily undergo addition reactions. So an addition reaction is where you break a double bond and then you replace the double bond with 2 other atoms. That's not going to happen with benzene. Alright, so if we look at our structure right here, this is the first model of benzene was suggested by Kuckel, okay? And it suggested that it was in a ring arrangement with alternating double bonds. Okay, so this model explained some of the known properties. So why does benzene not have isomers? Because it's in this ring structure. But it didn't explain why it wasn't reactive, because what we know about these double bonds is that it's kind of easy to break a pi bond and then add atoms to it, but that doesn't happen with benzene. So what ended up happening is when we take benzene and then we put it into an IR spec, or we put it into an HNMR, or other types of spectroscopy, we see that even though the structure is this, we don't see these alternating single and double bonds. So technically we have resonance. So this is one of those things that they use to prove resonance. So in this model right here, and please never ever draw this structure on a test, okay? But when we look at this model right here, it's showing us that the electrons are delocalized. So the electrons end up going in between these different bonds, and that actually creates more bond strength. It makes a more stable compound. It makes it much harder to break that pi bond. So each of the 6 carbon atoms that you have are going to be sp2 hybridized. Okay, so sp2, so if we look at it, and I'm just going to keep drawing this over and over again. If we look at it like that, and we count the bonds, remember pi bonds are not hybridized. So if I look around each carbon and each one's the same, I have a bond here that's a sigma bond, I have a sigma bond here, so that's 2, and then I have another sigma bond here, that's 3 places, so 3 sigma bonds, 0 lone pairs, so I need 3 places for the electrons. It's sp2 hybridized. Well, that means that there's a p orbital that's empty. So because you've got that p orbital that's empty, that makes it easy for the electrons to like switch between the bonds. And it actually does have a planar shape. So all of these carbon atoms are going to sit flat on a plane. So since you have this sp2 hybridization, you're going to have 1 pi or 1 p orbital open. I'm going to show you what that looks like. Hold on, let me actually go to that. Okay, so this is what it kind of looks like. So you can see right here we've got this p orbital that's in the y direction in this case. And what ends up happening is those electrons will actually go in between all of those orbitals and just keep moving between it. They're delocalized. Okay, so These p orbitals overlap and they in both directions, and then that creates this cloud where the electrons can just move. This is a very, very stable arrangement. It's very hard to break that pi bond because it's very stable. The electrons are just constantly moving and being delocalized in this molecule. Okay, so the bond lengths in between the single and the double bonds are going to be equal because there's resonance, since the electrons are moving between. So it's not going to be as long as a single bond, it's not going to be as short as a double bond, it's somewhere in between. Okay, so the delocalized structure is more stable than the Kekulé structure. So essentially, if you look at the Kekulé structure, this is the Kekulé structure. Okay, these alternating double bonds and single bonds. If you were to take the bond enthalpies of each of these bonds, so take the bonds, the single carbon-carbon ones, the double carbon-carbon ones, and then the carbon and the hydrogen bonds. And then if you were to add them up together, it would be less than the amount of energy that it would actually take to break this molecule down. This is a very stable structure because of the resonance. Okay, so benzene will react. It just does something called a substitution reaction. So essentially there's a hydrogen, there's a hydrogen here, not a carbon. The hydrogens can be replaced. So you can go on there and take the hydrogen off and then replace it with something else, like a functional group, like an alcohol, or you can replace it with a nitrogen. And then that's one of the reasons that benzene is so important, because we can use this as a precursor molecule for a lot of chemical reactions. So benzene will undergo substitution reactions where we substitute the hydrogen, but not addition reactions where we break that double bond and then add 2 more atoms.